All right, so today we're going to be discussing thermodynamics.
So in this unit, we will have several days, and today is the overview, and next time we'll also have a general overview with some applications, and we will also have systems in nonlinear dynamics, and then energy and conservation laws, and we will have a Kahoot to wrap it up. So some very important terms in this unit is system. So it's the space under observation. So in physics, we look at some systems, and we usually define them with force and in mechanics. And in this unit, we will also use system, and so we will um, investigate energy more easily. And there's a boundary, and it's what separates system from the rest of universe or surroundings. And we have open system, closed system, and we also have isolated system. It's just a theoretical system closed off from the rest of the universe. And then systems defined in terms of path-independent state variables. We use these variables P, V, T, N, and P is pressure, and V is volume, amount of space something takes up, and T is temperature. And temperature is the average kinetic energy of molecules in the system. So it relates to how fast they're moving and their kinetic energy, their mass as well. And then there's amount of substance that's in the number of moles. And moles are just units for how many atoms the substance has. And we have types of properties and processes. And properties can be extensive, which means they are dependent on extent of system like energy, volume, and mass. And intensive, it means that they're independent of extent of system like pressure and density. And processes, these are the regulations for which we are looking at the system. It can be isothermal. It means the system has the same temperature. It can be isobaric, the same pressure. And isochoric, which means it has the same volume, and adiabatic, which means there's no heat transfer, and then cyclic, which means system returns to original state after several processes.
All right, so what is heat? Heat refers to the energy transfer between a system and the surrounding due to difference in temperature, and there are a few key types of the heat transfer, right? You've heard of these probably in like elementary school, right? So like conduction relies on the direct contact, whereas convection relies on molecular motion, and radiation. And radiation relies on.
Has a good microphone. The D10 has a pretty awesome microphone.
Mm-hmm. Yes. So radiation relies. Should I wait for that to pass by, Mr. Norman?
That's funny.
I have a question. Can my D10 that shows the classroom come closer to the one that shows my sharing screen, because it's so far back that.
All right. For now, I muted the D10, and we will unmute afterwards. So, as we were saying, conduction relies on the direct contact, whereas convection relies on molecular motion. And then radiation is about like the source. You have rays, waves, or particles transmitted from that source. So that's heat. And it connects back to the previous idea of temperature. And the temperature is the average kinetic energy of molecules in system, right? So heat transfer occurs due to the differences in temperature. Now, what is work? So in thermodynamics, we have external pressure, and that external pressure applied will change the volume. And so this transfer of energy, we call that the work in thermodynamics. And so work equals pressure times volume is the key mathematical identity behind this concept here. And so we have the negative sign convention, but basically if you take like a volume pressure graph, then you can take the area under the curve of the graph, and that relates to the work done. Next, we talk about the key example of a piston for work. A piston, so here you can see there's ideas of pressure, right? And the external pressure. So if your pressure external is greater than the pressure of the gas within the piston, then compression can occur. And if the pressure external is less than the pressure of the gas in the system, then expansion will occur. And this actually ties back into work equals pressure times volume. So now we talk about some key sign conventions, at least like in chemistry and thermodynamics, these are the key sign conventions. They change sometimes in different textbooks, but this is like the most common convention. Heat applied to the system will be positive, whereas heat released by system is negative. And similarly, work done on system is positive, and the work done by the system is negative. Those are some key sign conventions. And next we talk about the key ideal gas law. The key ideal gas law tells you that pressure times volume will equal to the number of moles times some constant. This R is called the ideal gas, the gas constant, the universal gas constant, and then T is just temperature, right? And so one thing you notice is that work is the pressure times the volume, right? So both sides of these equations are showing some form of work as highlighted here. And then, so if you have like three of the key state variables, right? Pressure, volume, number of the moles, and then temperature, then you can determine the other one, right? The fourth one, if you have three. And so if we have the same number of moles, right? In a few different systems, then the ratio PV divided by T will always be constant. All right, next, we're gonna basically end off with the first law of thermodynamics. We'll discuss a lot more in depth next time. It tells you that energy is neither created nor destroyed, but can only be changed from one form to another. So we derive on this idea of like energy conservation laws. And you use that like a lot in mechanics, right? And even a little bit in electromagnetism, but mainly in mechanics. And like internal energy will remain constant unless transferred via heat or work. That's what this second equation down here is saying. And the change in the internal energy is just heat plus work. So internal energy is the kinetic energy plus potential energy of the system. And so now we have the change in the internal energy is equal to heat plus work, according to the first law of thermodynamics, right? Because the energy transferred is just via heat or the work. So change in the internal energy is heat plus work. And so one application of first law of thermodynamics is that there's no such thing as perpetual motion machine. And we'll have a slide on that next time as well. But that is one key portion of the first law of thermodynamics. So that was basically all the material that we had to cover for today. I'll see if I can find a quick demonstration to present. As of now, I'll also be entertaining some questions in case anyone has questions about the introduction to thermodynamics. All right. So I think we could try to look a little bit at an activity. So in molecular workbench, I can go back a little bit. In molecular workbench, they have a lot of cool tools and activities here. And one key activity is on the heat and temperature. So we can look a little bit through that. So here they teach a lot of really cool things with their demonstrations, right? So here we have like heat and temperature. This is talking about temperature and what we were discussing regarding temperature, right? That it's average kinetic energy. So you can click to start and stop in this. And I think they have different examples here, so what they're showing. So they have like stuff with increased temperature and there's more kinetic energy for the particles. And I think they're doing this for the 4 seasons. All right, here they're telling you that temperature is about kinetic energy and not just speed. And so they're gonna show like different substances to demonstrate this property, right? And so here they have a quick question answer. Temperature of substance is related to, is it only the speed of atoms, the mass of atoms, both speed and mass of atoms, neither the speed nor the mass? To see that you're paying attention, try to put like the answer to that in the chat. Which one would that be? Is that A, B, C, or D? All right, so as you can see, so the answer would be C in this case. I was having some brief issues with chat earlier, but those are fixed. So the temperature of the substance is related to both the speed and the mass, right? Because it's dependent on the kinetic energy, which is 1/2 mass velocity squared, and not just the speed, right? And so they show that a little bit in these different substances with like different masses, how the temperature will change. All right, so they have a lot of nice demonstrations regarding this average kinetic energy and temperature. So let's move a little bit ahead. All right, so here they talk about heat conduction. And so the process of heat transfer giving energy by atoms that have higher kinetic energy to those that have lower kinetic energy, right? And so it goes back to the idea that there's differences in temperature, right? Differences in the kinetic energy. And so when the temperature becomes equal, the heat flow will stop and then thermal equilibrium will be reached. And so they're going to show that in this demonstration. If we run the demonstration right now, they show some ideas of that in the demonstration. So they're showing how 2 objects are going to reach thermal equilibrium. And you can see this graph, right? How the top branch here and this bottom branch here is going to converge to a constant value. And so, these are some of the key ideas behind heat conduction here. And the idea that equilibrium is reached. We're going to talk a little bit more about conduction next time as well, and the specific mathematical ways of describing conduction. We also have thermal radiation, which is where the energy is radiated from a source, right? So when we burn wood, it emits some invisible energy packets called photons. If you remember, like back in quantum mechanics at the beginning of the year, we discussed this, like the quantum mechanics and optics, we had some discussion about photons. And so they have, so in this demonstration, we can see the ideas of radiation and photons traveling. So we can heat the, and so this is gonna emit some photons. There we go. So if we heat it up a little bit, then you can see that it's emitting the photons, right? And that's increasing temperature on the left side here. So that's a key idea behind radiation and photons emitted. All right. And then this is just showing heat in terms of energy now. But this is a very good visual diagram here. And it talks about internal energy. Right? We're talking about this with the first law of thermodynamics. Internal energy is the sum of the kinetic energy and the potential energy, right? And so we can see the temperature, everything correlating to like temperature rising, thermal expansion, and phase change via this visual diagram. Take a moment to look at the visual diagram. All right. And then here, I think at the end, they keep like a reflection. They keep like a reflection where you can like create some responses. What is true of the kinetic energy of each individual atom when a substance has reached a certain temperature? And which of the following means of heat transfer explains why? All right. So let's look at the question on the left. Take a minute to try the question on the left and answer in the chat. What is true of the kinetic energy of each individual atom when a substance has reached a certain temperature? The kinetic energy of each atom is the same as every other atom. The average kinetic energy of each atom is the same as every other atom. Some atoms have higher average kinetic energy, or some atoms have lower average kinetic energy. Try this one out. All right, so we have three answer choices. Oh, wait, I don't think, okay, so these ones aren't actually graded. So I think it is B. The average kinetic energy of each atom is the same as every other atom, right? So temperature relates to the average kinetic energy of the atoms. And so which of the, so if Jane's hand was burned after she touched the pot, then this is just conduction, right? Which is just by a direct heat transfer. They don't have, I think this is to create like a report or something. This is like the summative activity at the very end. All right. So that concludes it. So I recommend you check out like Molecular Workbench. You can try like a few activities. They have a few demonstrations which are pretty complicated. We might include one of them later, but it's really nice to try out these activities, right? And really get a feel for some of the key concepts. And so, yeah. Are there any questions regarding thermodynamics? All right. If there are no questions, so we covered like a bit this time. If you're expecting a bit more, then we will definitely talk in a lot more depth next time regarding thermodynamics. A little bit of mathematics will introduce a few more laws, concepts, and ideas. So return next time to learn a little bit more about thermodynamics. Thank you so much, everyone.
Yeah. Yeah, please reach out to us if you have any questions. Yeah, have a nice day. Thank you, Rohan.
Yeah, I have